Our lesson for today is going to be a fairly short one. We're going to be talking about the structural effects on acids and bases. So, for acids, the weaker the HR bond, in other words, the weaker the bond between the H plus on the molecule or the hydrogen and the rest of the molecule itself, and the more polar that bond, then the stronger the acid. So strong acids have very polar hydrogen to the rest of the molecule bonds, and the bond is very weak because when you put a strong acid into water, that hydrogen breaks off of it. So stronger acids, that hydrogen breaks off more easily. Uh, Hydrogen carbon bonds are nonpolar and they're very strong. So hydrocarbons in general, just like methane, CH4, that's not an acid at all. Hydrogen fluorine bonds are polar, but they're also very strong. The hydrogen fluorine bond is very strong because the hydrogen and fluorine atoms are very, very small, so they get very close together and form very strong interactions. And so, hydrogen fluoride, despite being incredibly polar, hydrofluoric acid is a weak acid. Whereas, for instance, hydrogen iodine bonds are polar and they're weak. There's a huge difference in electronegativities between hydrogen and iodine. Uh, it's also a fairly weak bond between those. So, hydroiodic acid, and really hydrogen with all of the other halogens, is a strong acid HCl, HBr, HI. And then for oxyacids, which are, as you might guess, acids with oxygen in them, the more oxygens you add, the more polar that hydrogen oxygen bond becomes, and the stronger the acid is. So, we're going to take a look at some examples with that. So, here I have five different acids that contain hydrogen and chlorine. We have hydrochloric acid, which it has a very large Ka because this hydrogen chlorine bond that we have is very weak and polar. Now, in these other acids here, these are oxyacids. Despite how the formulas may be written, the hydrogen is connected to an oxygen. Then you have a chlorine, and then if there's other oxygens, the other oxygens are attached after that. For halogens, if you had bromine or iodine in here, like for chlorous acid, you could have bromous or iodous acid. You could have perbromic acid as well. Um, you can't get these with fluorines, however. But for any of these acids, essentially, you'll notice the acid strength goes from uh, HClO, 3.5 times 10 to the negative eighth. That's a very weak acid. Whereas perchloric acid, its K is very large, and chloric acid is one that you're almost never asked about because it really straddles the line between being a weak acid and a strong acid. But what happens is, as we add more and more oxygens onto the chlorine here, over here, these oxygens are electronegative. And so it's going to kind of pull the electrons towards that end of the molecule, and it will kind of weaken the bond between the hydrogen and the oxygen by polarizing that molecule more, by polarizing that bond. When you have two oxygens attached, it's going to be pulling electron density that way. And when you have three oxygens attached here, that's really going to start pulling the electrons towards that end of the molecule, and it will kind of weaken the attraction between the hydrogen and the oxygen, such that with perchloric acid, it breaks apart quite readily as soon as you put it into solution. These being very electronegative, this also helps to stabilize the conjugate base that's left over because when you lose the H plus, you're leaving behind an electron. And so it helps if you have a lot of electronegative stuff there to make that conjugate base very stable. So the other part to this is that stronger acids have more stable conjugate bases. that are quite electronegative and can handle that excess of negative charge that builds up on them. So take a look at these two acids. We have nitrous acid and nitric acid. See if you can predict which one of these would be the strongest acid. Well, nitrous acid has a Ka of 4.5 times 10 to the negative fourth, whereas nitric acid has a Ka that is large or much greater than 1. And this is once again because the addition of the oxygens essentially weakens the attraction between the oxygen and the hydrogen, making that hydrogen pop off more easily in solution. And producing H pluses in solution is the hallmark of a strong acid. So, just to kind of summarize all of that, conjugate bases typically end up having a negative charge because you've lost an H plus, you lost the hydrogen, but not its electron that it had. The presence of very electronegative elements in the conjugate base makes it more stable than the acid, making the acid stronger. And keep in mind, stronger acids have weaker bonds between the hydrogen and the rest of the molecule. So I hope that kind of clarifies things a little bit for you. And with that being said, I hope you all have a great day.